Hi everyone, welcome to the second installment in Online Stats. What we're going to do today is have an introduction to the t-statistic, which will be used to do t-tests, which are very similar to z-tests, just another version of that. To get started, I think we need to know what t is, when and why we would use t instead of z, and then we'll talk briefly about how to work with a one-sample t-test, and I'll produce a different video where we'll actually go through a couple t-tests. So, to get started, what is t? T is a standard score, and if you would remember a few weeks ago when we introduced z, z is a standardized score. So we're going to use that as a reference. In fact, this slide should be called just like z. So t is a standardized score. T is used with normalish distributions. And I say normalish because of central limit theorem, we can actually have some flexibility. It needs to be close to normal, just like z. What t measures is the distance of a score from the mean, and it does so in units of standard deviations. Remember the definition of z? That's exactly what z does. Let's see. That's a t-distribution right there. The t-distribution has a mean of 0 and a standard deviation of 1, just like z. So as I said, the slide should have been called just like z. But I wanted to point out the similarities because we really use it in the exact same way that we use z. So the question is, well, why then don't we just use z? Well, I want to take you way back to when we first talked about dispersion and variability to kind of explain that. First of all, z is applied to situations where we know a population, and so we would have mu and sigma. And if you remember when we did our z-test, we used the population here, we were able to calculate the mean and standard deviation of that. And so I want you to think back to when we learned standard deviation. So the standard deviation formula for a population is this value right here. That's the sum of squared deviations, sum of squares, over n. However, there are times when we don't necessarily know the deviation of a population, which is okay because we can estimate it using the sample standard deviation. So do you remember the standard deviation formula from a sample? That's it right there. So here we have S. We have the sum of squared deviations again, the sums of squares, except this time, when we're estimating it, we use degrees of freedom. So here in a sample, we use n minus 1 as opposed to n. And that's because when you're estimating a standard deviation using the sample, you're at risk for underestimating the actual standard deviation of the population. So what that formula does, that n minus 1 makes that number smaller, which increases ever so slightly the size of your estimate, and that corrects for the error. So, why not just use z? Well, here's the thing. When we're dealing with small sample sizes, that's what this is saying right here, when n is small, we're dealing with small sample sizes. The sampling error is a lot bigger. When we're dealing with an unknown sigma, we're having to make an educated guess. And in both of those situations, if we were just to pretend everything was okay and use the z distribution, we would sort of be lying to ourselves. We need to use an adjusted distribution, which is more conservative, and that helps us be safe when we make estimates. So what this graph shows right here are 3 overlapping curves. This one right here in red shows what the t-distribution looks like with 10 degrees of freedom. That would mean that there are 11 people in our sample. Notice what happens if we go to a t-distribution with 20 degrees of freedom. So that would be 21 people in the sample. So 21 minus 1 is 20. And you can see that the red line is a little bit shorter and wider. The blue line shows a normalish curve that's taller and thinner. And then if we have a t-distribution with infinite degrees of freedom, it's actually the same as the standard normal distribution. In other words, as these numbers get bigger, your sample size gets bigger. I'm going to do something with my hands here. T grows up into the Z curve. So they literally become the same thing. Actually, it only takes about 150 in the sample before they're indistinguishable. So because of that, a lot of things like SPSS or Excel, who do the software packages, actually don't even use the Z-test. It always does a t-test just because it's slightly more conservative and reduces the risk of errors. So what's the difference between T and Z? It's really just that T is used if you have a very small sample size and if you don't know the population standard deviation. And why? It's because it makes it it reflects the fact that small sample sizes have larger error. All right, so a lot of similarities there. As we move into the concept of a z-test, the t-test, the t-test has only two differences from the z-test. So if you're able to do those z-tests okay, the t-test is not going to be a big deal at all. And here are the two. They both start out with step 1, exactly the same. But step 2, what we do in the z-test is we look up a critical value of z in our z-table. Well, here we're going to be using a t-table to look up a critical value of t. Not much difference there, right? In step 3, we calculate our test statistic, z-test. And the formula for that is our sample mean from our study compared to the population mean divided by the standard error. Well, in the t-test, not surprisingly, we calculate a t-test statistic. And if you look at this formula, it's the same numerator. It's just the distance between mu and m. And here it's divided by standard error. Only difference is here the standard error is calculated from the sample standard deviation. Here it's calculated from the population standard deviation. So it's really conceptually the exact same thing. The adjustment has been made as soon as you calculate standard deviation. All right, so the next thing you'll need to know is a little bit about how to use a t-table. I'm including a t-table in Moodle, and if you want to go back to our old folder, I'd already included one in that. And this is a copy of the exact t-table. In this t-table, we will be using this row right here and these degrees of freedom in step 2 to calculate or to identify a critical value of t. So let's go back over here. In step 2 of our test, that's where we calculate or select our alpha. I'm going to use 0.05, and we're going to look at our degrees of freedom. So usually we will use an alpha of 0.05 split into two tails. So if you look at this, you see this is my alpha level for two tails, 0.05. So I know that's the column I want. And in our in-class examples, I think we've been having 5 people. So if that's the case, our degrees of freedom would be 5 minus 1 or 4. Just go see where those two match up. If you look in the table, that's 2.776. And in APA style, the way you would see that written is just T critical. The parentheses there show our degrees of freedom. So that says 4 degrees of freedom. And that is plus or minus 2.776 T. So that would be our critical value for our test. Now, we've talked about the law of large numbers and the central limit theorem, so I want you to think about this for a moment. When we had a critical value of 2.776, we found that with 4 degrees of freedom. What do you think would happen if we used a larger sample size, like n of 11? Well, here's another example of how t changes. Notice that with a small degrees of freedom, it's shorter and wider. As degrees of freedom increases, there's less in the tails and more in the body. Okay. All right, so what happens if we increase the sample size? Let's go back to our table. Keep in mind that with the degrees of freedom of 4, we had 2.77. But if I use n of 11, still using the same column here, but I have 10 degrees of freedom, and we meet right there. So in APA style, I see critical value of t with 10 degrees of freedom is 2.228. Because that curve has gotten taller and skinnier, the critical values are actually getting closer, a little bit closer to 0. Now, we don't do this over and over again. This is just an exercise. Anytime you do a study, you try to start out with a large sample size. You do that, and you calculate what you have. So we're just going to run through this as an example, though, so you can see how degrees of freedom changes. So real quick, let's look at this. Let's see. What if we had degrees of freedom of 300? Look all the way down here. Our table only goes up to 120, but if you come down here to anything above 120, notice that this is 1.96. Does the number 1.96 sound familiar? If you flip back to our z-test, the critical value for z with an alpha of 0.05 and 2 tails, it's 1.96. So seriously, by the time you get over 150 degrees of freedom, this is literally the same thing as a z-test. Mostly important when you're estimating the sample standard deviation with a low sample size. So to kind of wrap this up, which test do we use? We're going to have 2 tests in our tool bag here. We'll use a one sample z-test if we know a lot about a population, if we know both the mean and the standard deviation, and we want to see if our sample mean is likely to have come from a different population. To go back to this and Cassie's hypothesis, we wanted to see if the population of stair climbers was different than the population of resting heart rates. So today we're just introducing a new idea to find out if it's significantly different. So today the new idea is if we know just a little bit about a population such as mu, but we don't know the standard deviation, or if we're dealing with just very small samples, it's also good. And we want to see if our sample is likely to have come from a different population. We want to know if it's significantly different. So what I want you to see is the context here is the same, almost the same, in that both cases the z-test or the t-test is used to see if we want to find out if our sample is somehow different. The only difference is we would use the t-test if we only have mu and have to use the standard deviation from the sample. So in closing, if you look at these formulas, you see they're the same thing. The tests work out the same. The 4 steps of a t-test are the same. See if the means are different. We set up our criteria, calculate a test statistic, and we make a decision. I'm going to wrap that up here, and I will use a different video to actually work through a solution. Hopefully you can follow along. And I think you'll see it's a pretty easy solution.